Assalamu alaikum. Today we'll be discussing chapter number 35, that is related to optics, and this is the first chapter of optics. We'll be briefly going through what is light, then reflection, refraction, and then dispersion, and then total internal reflection. So these are the main articles which we'll be covering in this chapter. So starting with what is light. It's a form of electromagnetic wave which does not require any material medium to move through from one point to another. As we have sunlight, and sunlight is an electromagnetic wave which travels from sun to earth without any material medium involved. That is, it travels in a vacuum. In some cases, it acts as a particle. Light, as now we all know that it has dual nature. That is, at some point it behaves as a particle, and at some it acts as wave. The most famous experiment in which we consider light to be made up of particle is photoelectric effect. We have already done the experiment related to photoelectric effect in our labs. In some cases, it acts as a wave, like in case of interference. When we get different interference pattern, there the light is acting as a wave. The quantization model assumes that the energy of a light wave is present in a particle called as photon. That is how we usually define light. That light is consists of a bundle of photons, and photons they don't have any charge on them. They are neutral particles, and we can find the energy of photon by using E equals to HF, and H is a constant, so energy is directly proportional to frequency, and H is the Planck's constant, whose value is 6.16 returns for minus 34 joules second. Also, we can show this energy in the form of lambda, that is E equals to hc over lambda. Light, now we know that light has dual nature, and this was told us by De Broglie, who performed an experiment and showed that light has dual nature. Speed of light was found out by using two different methods. One is Romer, and the second one is Fizeau's method. They performed separate experiments, and by performing these experiments, they concluded that the speed of light is 3 into 10 power 8 meters per second. Now, considering these three conditions, suppose we have a slit, and a light coming towards this slit, and we have a small opening, and the opening is represented by D. So the light with wavelength lambda is traveling towards the slit. If the wavelength is very smaller than this opening, that is D, then the light will move in this way, that is in the form of a wave it is traveling previously. But if lambda is equals to D, that is comparable to the opening over here, then if the light wave is moving towards the slit in this form, and it will move in the form of wave fronts, and it will take this shape over here. And if lambda is very greater than the slit opening, then we will have again a wavefront after the light is passing through the slit. So in the first case, we will say that it will continue to move in a straight path. In the second case, ray spreads out, and in the third case, there is a point source emitting spherical waves over here. Now we'll move to the article reflection. Reflection is when a light ray is incident upon a medium. So this incident ray, when strikes this other medium, it reflects back. If The important thing is that two mediums must be different. Suppose that this medium one is air and the second medium is glass. So when this incident light strikes this medium over here, the interface of the medium, it will reflect back. And the important point is that all the incident, the normal and the reflected rays, they must all lie in the same plane, and angle of incident must be equal to this angle of reflection. And this is also known as law of reflection, that is angle of incident is equals to angle of reflection. There are two types of reflections. Number one is specular and the other one is diffusive. Specular reflection is when light is reflected after striking a smooth surface, and diffuse reflection is when the light strikes a surface, a rough surface, then we get diffuse reflection. When the light hits a smooth surface, all the light rays after reflecting move in the forward direction, and if we are to make an image of an object which is being placed in front of us, and we have a smooth surface through which the light has to reflect, then we won't be able to get a clear image of that object, because all the light rays, they will after striking this smooth surface will move forward, and very few of the rays after striking some rough part of that surface may enter our eyes, so we won't be able to make a clear image of the object placed ahead of us. This is the only reason that we are not able to see clear on rainy days, because when rain falls, we have water on the road, and the water is considered to be the smooth surface, and after our beam falls on the water, all the rays, they move forward and it does not give us a clear image. Whereas in case of diffuse reflection, when the light strike this rough surface, you can see that the after reflection light is going, the reflected light is going in all different kinds of direction. So there is a chance that we may our retina may receive more rays, reflected rays, and we get a better image of the object which is placed ahead of us. Uh, there is another type of reflection known as retroreflection. Retroreflection occurs when a surface returns a large portion of light beam back to its source. So after reflection, all the light is reflected back to the source where it originated, and this gives us a very clear and very sharp image. Uh, the retroreflection principle is mostly used in traffic signs and in cat eyes or the separators. Most of these studs, they use this principle of retroreflection. Okay, the next article is refraction. What happens in refraction is that when a light is incident on a medium, and there are two different mediums again, and let us suppose again the medium one is glass, and medium one is, sorry, air, and medium two is glass. So when this incident light, it strikes this interface over here, a part of this light is reflected back, but part of this ray enters the second medium and is bent towards the normal, and this bending of light in the second medium is known as refracted ray. So here we have an angle of incidence, and this is the angle of reflection, and this third angle with the normal is angle of refraction. So when light travels in a medium and strikes the surface of another medium, a part of it is refracted and a part enters in the second medium, deviating from its original path. This is how we are going to define refraction. Angle of refraction depends upon the properties of the two media. And we mathematically we can write it as sine of theta 2 over sine of theta 1 equals to v2 over v1, which is equals to constant. And now this v1 we'll consider it to be speed of light, and v2 is the speed of light in medium 2. Path of light ray through a refracting surface is reversible. So if we look at this figure over here, if this incident light falls over here and enters the medium and is refracted in this path, so now if we want to reverse this process, if we place this light at this angle over here and try to and instead of becoming a refracted angle over here, this is the angle of incidence, and we have a light source in glass medium now, then we will be able to get this refracted ray in air at the same angle. So this path is reversible. We can have the same path if we place the source in glass at the angle of refraction. If light enters a denser medium, then angle of refraction is less than angle of incidence. That is, the refracted ray bends towards the normal. And if we have a ray entering from rare medium from a denser medium, then the angle of refraction is greater than the angle of incidence. It means that it will bend away from the normal. So this is the case when we have air to glass, rare medium to denser, it is bending towards the normal. Glass to air, incident is from the glass, so it is bending away from the normal over here. Index of refraction is defined as a speed of light in vacuum to the speed of light in medium. It is denoted by n, and n is equals to c over v. As it's a ratio between two speeds, so angle of the refractive index does not have any units. As light travels from one medium to another, its frequency does not change, but its wavelength it does change. So whenever the light is entering from one medium to another medium, this frequency will not change, but the wavelength will change. So we can write this v equals to f lambda, and if we are considering two media, then v1 equals to, as frequency remains constant, f lambda 1, and v2 equals to f lambda 2. And now as we have f constant, so we can write v1 over lambda 1 equals to v2 over lambda 2. And from here we know that n is equals to c over v. So for both the media, c over n1 is equals to v1 and c over n2 is equals to v2, replacing the value of v1 and v2 over here, rearranging this equation over here. So after rearranging, I get lambda 1 over lambda 2 equals to v1 over v2, putting in the value of v1 and v2. We get lambda 1 over lambda 2 equals to n2 over n1, or n1 lambda 1 equals to n2 lambda 2. Generally, we can write this as n equals to lambda over lambda n. So n can be any number over here. Also, we know that sine of theta 2 over sine of theta 1 equals to c over n lambda multiplied by n over c, n1 over c. So cancelling the c from here, we get n1 over n2, and rearranging we get n1 sine of theta 1 equals to n2 sine of theta 2. This is Snell's law, and Snell's law is considered to be the basic unit of optics. It is very useful in solving many of the optics problem which are being solved nowadays. dispersion and prism. Dispersion is known as splitting of light into different wavelengths, and index of refraction generally decreases with increasing wavelengths. So it means that violet bends more than red light, and we also know that wavelength of red color is greater, and whereas the wavelength of violet, it has the smallest value, and it goes in this way: red, orange, yellow, green, blue, indigo, violet. uh, all of you must have seen prism. Prism is a transparent optical element with flat polished surfaces that refract light. At least one surface must be angled. So if we stick two flat surfaces together, then it won't be a prism. For prism, one surface has to be angled. uh, Angle of deviation is a ray of a single wavelength of light incident on prism emerges refracted from its original direction of an angle angle, this delta over here, called angle of deviation. So if you see that we have this ray incident over here, and the original path of the ray is in this direction, but after entering the prism, it is refracted, and then again it enters another medium, that is from glass to air, so it will move in this direction. So if I draw an angle from this original path to the refracted path, we say that this is the angle of deviation, and this is the amount of angle at which the ray has deviated from its original path. Now, total internal reflection. Total internal reflection can be understood by using this figure over here. Now, you see that we have a source over here, and we have glass and air as media. Source is placed inside the glass, and now this ray will originate, light ray will originate from glass, and there are 5 possibilities in which the rays will move. First is that this ray will move straight and enter from glass, it will enter air. In the second case, it will move in such a way that we have this incident angle, and when it enters this rare medium over here, it will move away from the normal, and this is the case we will have for ray 2. Now if we keep on increasing, and now if you draw a normal over here, and you see that incident angle has been increased, and again this angle of refraction, the ray is bending away from the normal, and it is also increasing. In the fourth, you will see that this is the case when this angle of incidence is equals to the critical angle, that is theta c over here. This, at this critical angle, the ray, the refracted ray, will move at an angle 90 degrees to that of the normal. So it will move at 90 degrees over here, and you say that this ray is refracted at 90 degrees to the normal. Now, if we further increase the angle, the incident angle that is greater than that critical angle over here, this is the critical angle at which the ray is reflected at 90 to the normal. So now if I increase this incident angle further, that is greater than the critical angle, what will happen is that when at an angle greater than this critical angle, it strikes interface of the two media, it will reflect back into the glass, and we get total internal reflection. So we always get total internal reflection when the incident angle is greater than the critical angle over here. So this is how we get total internal reflection. The most important application of total internal reflection is in fiber optics nowadays. So using Snell's law, n1 sine of this critical angle equals to n2 sine of 90, and sine of 90 is 1. So n1, this critical angle equals to n2. So to find the critical angle, we have sine theta c equals to n2 over n1, where n1 is greater than n2. Fiber optics again is an example of this total internal reflection. So this is all about the important features of chapter number 35. I hope you will understand the basic optics and basic simple rules of reflection, refraction, dispersion, and total internal reflection.